Hey guys, welcome back to chapter 4. I just want to let you guys know that I really appreciate all the feedback emails that I have gotten from you guys and am very thankful for the suggestions. And I do have one thing that I need to tell you. I realized I thought you guys could see me while viewing the slides, but apparently you cannot. And I have IT actually working on that. Hopefully that will be resolved for chapter 5. But I wanted to go ahead and finish up chapter 4 for you guys so that you would have this chapter. A reminder that the first exam is coming up and it's going to cover chapters 1, 3, 4, and then part of chapter 5. And remember, I will have a review for you guys that will be coming after we finish that chapter 5 together. So I'm hoping you guys are having a great weekend, and I just wanted to go ahead, like I said, and get up the rest of 4. Even if you can't see me, I know that you can hear me, and we will get that remedied for you guys. So we left off last time, if you remember back, we were talking about some of the things that prokaryotes have that eukaryotes do not. And we were kind of looking at the idea of some of those special things that prokaryotic cells have, particularly those of bacteria. We looked at things like the capsule, and we looked at things like the flagella and the pili and the fimbriae. We're going to pick up with talking about the cell wall, and please forgive me, I have a little bit of a scratchy throat. I was telling David earlier that I wasn't really sure if I was going to be able to lecture this weekend, and so he assured me that I should probably just save my voice and rest, and then I could lecture for you guys. So I've been sitting very quietly. So I think he loves you guys because I have not hardly talked at all this weekend. But we're going to pick up with the cell wall. I've said several times that the cell wall is very important when it comes to bacteria in particular. Remember, I told you guys about that peptidoglycan and the idea that if you're going to be a bacteria, you have to have peptidoglycan in your cell wall. If you don't have peptidoglycan in your cell wall, you are not a bacteria. And I also told you that we were going to talk about the difference between gram-positive and gram-negative cells, and that's a huge step when it comes to identifying microorganisms. And the major difference, as I said, was within the cell wall. So the cell wall is responsible for the shape of the cell. It does help to regulate water movement. Remember, the movement of water is called osmosis. So if too much water rushes into a cell, or if too much water rushes out of a cell, the cell will actually either shrivel up and dehydrate, or it will blow up and rupture. So the cell wall is responsible for maintaining those boundaries of water. We know as researchers the importance of the cell wall, and so many drugs target the cell wall because if you punch holes in that cell wall, that bacteria is dead. It does not survive. So some of the drugs that do this that you probably know of, amoxicillin, ampicillin, augmentin, penicillin itself does this. Think about some of those cephalosporins like Keflex or cephalexin. All of those are designed to target the cell wall of a bacteria. When you look at what peptidoglycan is, this is kind of the arrangement of peptidoglycan. It doesn't look like much. It is a polymer of disaccharides linked together by polypeptide bonds, but it is vital when it comes to the structure of a bacteria. When you look at the difference between gram-positive and gram-negatives, there's some major differences between these two. I'm going to start with the idea of what a gram-positive cell is. Gram-positive cells, when you look under a microscope after it has been gram-stained, is what color? Right now you should be saying purple. Are you saying purple? Because that's what color they are. When you look under a slide and you're wanting to see that on a microscope, it should be purple if it's gram-positive. Well, gram-positives have an extremely thick peptidoglycan. It's a really large chunk, if you will, of peptidoglycan. And embedded within that are teichoic acids. And these teichoic acids play a very important job of regulation. They move things into and out of the cell, especially those positively charged ions called cations that are going to be moving in and out of the cell that have to be regulated. So teichoic acids do that. Gram-negatives, on the other hand, have a rather thin peptidoglycan wall. The peptidoglycan is not what makes them necessarily gram-negative versus gram-positive. Both of them have to have peptidoglycan if they're going to be a bacteria. But gram-negatives don't have any teichoic acids. Instead, their regulations and permeabilities are due to what's called porins. These are channels that are formed that help to regulate. The special thing about gram-negatives, though, is they have what is called an outer membrane. The outer membrane of a gram-negative is actually made up of a lipopolysaccharide. The lipo portion, the lipid portion of this, is a lipid called lipid A, and that is an endotoxin that is wicked. Gram-negatives are not something that you guys want to be messing with. They are a very, very dangerous type of toxic bacteria that are actually very difficult to treat. One of the things we find about gram-negative bacteria is our immune system does not fight them off exactly the same way as gram-positives. Gram-negatives are much more difficult for our immune system to find, to hunt down, to target, and then to ultimately destroy. We also find that due to this outer membrane, it is very difficult for us to find antibiotics that will treat these. In a way, the outer membrane acts as a barrier for antibiotics. Antibiotics to treat gram-negatives have to be very small and they have to be hydrophilic. So you're saying to me, well, that's easy. Let's make them little and let's make them love water. Well, yes, that sounds easy, but it's not quite as easy as it may sound. These are really nasty little bacteria that can cause some major damage. And lots of septic patients, you guys know sepsis is when bacteria start growing in the bloodstream. A lot of septic patients, though, end up being in gram-negative septic shock. If you'll look back over here on the side of gram-positives, though, I wanted to point out that statement that says acid-fast cells. Now think back when I told you just last chapter when we were talking about the gram stain. I told you that there was an issue with Mycobacterium tuberculosis. Mycobacterium tuberculosis is a specialized type of cell because it does not follow the gram stain. Remember, it is a gram-positive cell, but it stains pink. And is that correct? The answer is no. No, 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 no. That is not correct. Gram-negative should stain pink. And I also told you, therefore, that it has to have a special stain called acid-fast. Well, the reason why these microbes like Mycobacterium tuberculosis don't stain the way they should is because inside of their cell wall they contain mycolic acids. These mycolic acids, in addition to the teichoic acids, regulate the cell wall a little different with how they uptake the stains. And so these mycolic acids, when they're found in a gram-positive, even though they're still gram-positive by nature, they don't take the gram stain the same way. So that little statement there about acid-fast cells and mycolic acids, that's talking about those specific cells that don't quite follow the gram stain rule, like Mycobacterium tuberculosis. This is a characteristic drawing of a gram-positive cell, where you can see those teichoic acids embedded there within you can see the wall there of teichoic acids, and you can also see the peptidoglycan. There's a really thick type of peptidoglycan. Gram-negatives, on the other hand, we're going to be taking a look at some of these in particular a little bit later on and talking about just how much of a protection this outer membrane provides them against our cells like phagocytes, against some of our immune complexes like complement, and then our ability to treat those with antibiotics, as I said, is sometimes a little bit limited. this is a look at that separation there between the plasma membrane and the outer membrane. You can see separated there by actually a thin layer of peptidoglycan. So let's go back and take a look at the gram stain then, because remember I told you, and I'm going to walk you back through this, but remember I told you that the first thing that you do in a gram stain is you're going to add crystal violet. And crystal violet, when added to both gram positives and gram negatives, when I hit the pause button and I take a look under the slide, both of those are actually purple. I then told you we add our mordant, and for us our mordant is iodine. And when I pause right then, both gram positive and gram negatives are purple. But then I told you we add our decolorizer. And the thing about the decolorizer was, I told you at the moment when I add the decolorizer, if I hit the pause button, gram positives are still purple as they had been the entire time, but gram negatives were colorless. Let me explain to you what happens with alcohol that is different on the cell wall of a gram-positive species and a gram-negative species. A gram-positive species, when you drop that alcohol on there, it actually dehydrates the peptidoglycan. When you dehydrate peptidoglycan, it makes a sealant. It seals everything inside. Now, that means that things on the inside can't get out. That does not mean that things on the outside can't get in, because they still can. But things on the inside, if they're sealed on the inside, that means that that crystal violet is actually sucked inside there and it is sealed within and cannot leave, so that's why it is purple. On the other hand, when I add that alcohol to the gram-negative species, what it does to the outer membrane is completely different. It actually dissolves part of the outer membrane. And when you dissolve part of the outer membrane, it leaves these little porous holes within the membrane. So anything on the inside very quickly floods out. Well, if I lose all of my stain from the inside of the cell, what color is it going to look? Well, it's going to look colorless because there's no stain within it. So this is why we see a difference based upon the cell wall between a gram-positive and a gram-negative. So now we have the gram-positives being purple and the gram-negatives being colorless. And so we add that secondary stain, which is a very basic stain called safranin. Safranin is that bright, deep crimson red color. And so when we add that, it actually goes inside of both cells. A lot of people think that safranin can't penetrate the gram-positive cell, but that's not true. But you have to think, purple is a very dominant color. And so with purple being on the inside of that cell, that's the color that you're going to see. It's going to mask over that pink color. However, on the other side with gram-negatives, there's nothing in there. All of the crystal violet washed out. So now when we add the safranin, that's the color that you see. That's going to be that nice reddish, pinkish color that you're going to be seeing with these gram-negatives. There are some that don't follow the rules. You know, I feel like everything I talk about, I'm always like, this is how it is. And by the way, there's some that don't do this. So I apologize, but we do need to know those atypical types of cells. And I'm only going to teach you one. I'm going to teach you Mycoplasma pneumoniae. Mycoplasma pneumoniae is an interesting one that I'm never able to really let down in my household. Let me tell you what happened here. So, my mom is a little bit of a hypochondriac. She does watch my children for me, and I'm very thankful for her and all she does. But, I mean, there's something, you know, she can be watching television and a disease come on television that's like the most rare disease in the Congos of Africa, and she'll look at me and say, you know, do you think I have that? I'll say, Mother, no. Have you been to the Congos of Africa? And she says, well, I kind of feel like I probably have that. So it's not anything new for her to come in and say something is going on with her health. So a few years back, she came in and she said, you know, I really don't feel good. I can't really breathe, and I just kind of have this cough. And I said, well, Mom, do you have a fever? She said, no, not too bad. I just don't feel good. So I said, well, I'm sorry. Sorry. Did you take anything? No, I don't think I need to take anything. So I leave and I go to work, and the next day, she comes to watch the kids, and she says, I just don't feel good. I just am having trouble breathing. So I sat there and I said, well, did you take anything? No, no, I don't think I need anything. So day 3 comes around, and here she comes. I really just keep getting worse and worse, and I really do not feel well. So finally I said, Mother, would you like for me to get my stethoscope and take a listen to you to make sure nothing's going on? And she said, well, now if it's not too much trouble. I said, no, it's not too much trouble. So I get out my stethoscope and I take a listen, and I could not believe it. She actually sounded terrible. Her lungs were awful sounding. She had some wheezing and a little bit of rattling inside there. And I said, Mom, you really should go to the doctor. Oh, dear. Is it serious? Do you think that I should probably just leave and go right now? So I had a short day that day, and I said, well, let me go get my work done, and, then you can go on to the doctor. So I feel really bad because when she got in there and she got an x-ray, she actually did have pneumonia, and it was an atypical type of pneumonia called walking pneumonia, and that's what you guys know as walking pneumonia is Mycoplasma pneumoniae. The signs and symptoms of that don't really present a lot like your typical types of pneumonias. And so, of course, the next day, well, it was the next couple of days. She didn't work for a couple of days, but the next couple of days, she came in and said, well, I'm glad that I'd almost died here with pneumonia, and you just kept telling me that I am fine. So now, still to this day, when she comes in and says she doesn't feel well, and I say, Mom, I'm sure you're fine, she says, do you remember when I almost died with pneumonia? So she didn't almost die with it, but it can make you very, very sick and not show those typical presentations. Well, it's also atypical because of its cell wall. It actually is a tiny little bacteria. It's the smallest that we study, and it doesn't have a cell wall. Now, you think about that. I have talked about the importance of a cell wall for bacteria, and now I'm telling you that this one doesn't have one. So you do need to know this for the exception to the rule. And also an interesting thing about it is it has sterols in its plasma membrane. And at first that may not trigger anything for you. But sterols are actually a eukaryotic type of proteins found in, proteins found in the plasma membrane. And this is not a eukaryotic species. This is a prokaryotic species. Therefore, sterols should not be found here, but they are. So that kind of helps to distinguish this just in the idea that it's one of the only places, only prokaryotes that you actually find these eukaryotic sterols. Another atypical cell that we've already discussed a little bit because you guys know about archaea, and you know the fact that they don't have peptidoglycan. They actually do have what's called pseudomurin, and that pseudomurin is really, really similar to peptidoglycan, but the big difference is that it lacks just a couple of things that peptidoglycan has, and so therefore can we say that it's a bacteria? And the answer is no, we cannot. Archaea are completely separate, and we know that now. I told you guys a little bit ago that if you damage the cell wall, then that particular species will die. Any type of medicine or chemical that can break down the peptidoglycan and leave these holes in the cell wall will kill that particular bacteria. Bacteria also have a plasma membrane. You guys have a plasma membrane. We talked about eukaryotic plasma membranes, so you know what those are. But those are layered up in a phospholipid bilayer. Remember, they have proteins embedded within them. We see that the proteins are what allow these to function. And so what we find about the plasma membrane is it's extremely important because these allow us to be able to be selective with what we allow into and out of the cell. That is highly regulated. And so if I mess with that regulation, if I alter the plasma membrane to where now all of a sudden we're not quite regulating as closely what's coming into and out of the cell, that in particular can kill the microbe, because we can't have certain quantities of things rushing into the cell or rushing out of the cell. So there are other drugs, antibiotic-wise, that also target plasma membranes, because if I punch holes in plasma membranes, boom, I'm dead. We do see within the plasma membrane, we're going to talk about a specialized group of bacteria that can actually do photosynthesis. Now, you guys know photosynthesis. That's where you take light and you convert that to energy. Most of the time, microbes have to have a chemical to convert into energy, but there's a very small group that are much like plants that can utilize light and convert it to energy, but they don't use chlorophyll. They actually have what are called chromatophores or thylakoids. If a microbe has chromatophores or thylakoids embedded within the plasma membrane, that particular microbe can actually utilize light as a way to get its energy. We have to be able to move things across the plasma membrane, and we talked about this in anatomy and physiology. You guys remember the difference between simple diffusion and facilitative diffusion, which are both considered passive, and then we have active diffusion. Remember, passive diffusion does not utilize any energy. We're going to move up a concentration gradient does utilize energy. So if I'm going down my concentration gradient, which is an area of high concentration, to an area of lower concentration, that does not utilize any energy and is considered passive diffusion. Think about riding a bicycle. This is how I think about it. I love riding a cycle as long as it's downhill. If we're going from an area of high level down to low level, it's kind of fun, right? You just jump on the bicycle and whee, away you go. Now turn that bike around. And now you're at the bottom of the hill and you're going to chug up that hill. That's not so fun. That's when I start getting off the bicycle and just walking. I'll just walk this bike up the hill, because it takes so much energy to go from an area of low concentration to high concentration. When we look at movement across this membrane, we have to be able, of course, to regulate water, because water for a microbe, they're very sensitive to osmosis, which is being permeable to the amount of water concentrated in an area so that we can move to be in equilibrium. We want our microbes not to have too much water, but certainly not to have too little water. And so we'll move water accordingly in order to be in that nice balance. I can put microbes in different types of solutions and actually see water moving either into or out of those species based upon the type of solution that we put them in. An isotonic solution is a solution where the concentration of water on the outside of the cell is equivalent to the concentration of water on the inside of the cell. So let me ask you this. If the concentration of water is already equal, which way is water going to move? It's not, right? Because if water trying to be in equilibrium is already in equilibrium, we don't have to move. If you take a look at the next one, we have a hypotonic solution. In a hypotonic solution, there's actually more water on the outside of the cell than on the inside of the cell. Well, if there's more water on the outside of the cell, water is then going to rush to the inside of the cell. Much like a water balloon that you hook up to a faucet, that cell is going to start to swell up. Now let me ask you this. What happens if I allow that balloon that's hooked onto the faucet to just keep getting bigger and bigger and bigger and bigger, and I never shut off the water? Well, it does stretch for quite some time, right? But eventually it will pop. And that's the same thing that will happen with this cell. It's called osmotic lysis. Osmotic lysis is when that cell is going to rupture and burst because there's too much water. Then we have a hypertonic solution, and in a hypertonic solution there is much more water on the inside of the cell than on the outside of the cell. And so what we find is that now to equilibrate, water is going to rush out of that cell. Well, when water rushes out of that cell, it dehydrates, right? Think about a grape and a raisin. P.S. I love grapes, hate raisins. Go figure. But anyway, a grape, when you look at it, it's like nice and plump and juicy. And then when you look at a raisin, it's like wrinkly and shriveled and sad, right? It just looks sad to me. Well, that's what happens with a cell. It's going to shrivel up and kind of shrink down because it's losing so much water. It's becoming dehydrated. And if you allow enough water to leak out of that cell, it will eventually die. It will dehydrate enough, and that's called plasmolysis. When we're moving with active transport, this means that we do require energy, which is ATP, and we're now going to be moving up that concentration gradient. We're going to go up that hill. We're going to go from an area of low concentration to an area of higher concentration. We do have a cytoplasm inside of prokaryotic cells. This is essentially, most of it is water, but there's a little bit of protein, a little bit of carbohydrates, and some lipids. This is the fluid portion that we see inside of the cell. We don't have a nucleus, but we do have what's called a nuclear area. And the nuclear area is simply a spot that you can see there, and it's where it's essentially where the DNA is located. We don't have a nucleus per se, but since we do have DNA and RNA, we know that there is at least an area for where that DNA is. Remember, it is a single circular piece of chromosome. They do not have any type of histones associated with those, and they do have what's called plasmids. The thing about plasmids that's interesting, it does. So with plasmids, you don't have to have them in order to live. They are extra pieces of chromosomes that are a part of the genetic makeup that you don't necessarily need in order to survive, but they're great to have. You can actually isolate these, copy them, replicate them. You can transfer those from one bacterial cell to another. And remember when we were talking about that pili, and I told you that we're going to make that connection between two cells. This would be one of the things that we could definitely transfer between one cell and another cell. And the question of, well, do I absolutely need it? The answer is no, but it sure does make life simpler. You know, my husband and I went out, we took the kids to a cabin for the weekend. And one of the things that we said was we're going to shut down all cell phones. We're not going to do any Facebooking. We're not going to do any emailing. We're not going to do any phone calls. We're not going to do any text messages. We are just going to be strictly family time. And it was Thursday, Friday, Saturday, and Sunday. You know, Thursday and Friday was great, and we all were very excited to kind of have that peacefulness. But then you start thinking, like, I really need to check my phone. I gotta check my emails. I wonder what's happening on Facebook. I haven't looked at Facebook. I have not looked at Instagram. I wonder what's happening. What's happening on Instagram? I haven't checked my emails. And so it was late one night, and I was up, and the cell phones, I knew where they were, and so I went in there, and I was really just going to check my emails for work to make sure that nobody needed anything or needed me, and I just turned it on, and here he comes, popping his head in the kitchen. He's like, "What are you doing?" So it's hard. You know, and I think, tell me this, what did we do before cell phones? How did we live? How did we drive? I have no idea. But if someone took my cell phone away from me today, would I die? Now, granted, I would not have any idea where I was going because all of my dates and appointments and everything I need is inside of that cell phone. So I may not know where I'm going, but would I physically die? The answer that I'm supposed to say is no. No, I would not. I'd be okay. I wouldn't make it without a cell phone. But it sure does make my life a lot easier. It helps me to organize things. It helps me to keep in touch with people. It helps me to do a lot of things on a daily basis. And so while it's not crucial for my survival, it's just really nice to have. So those things like antibiotic resistance, those things like being able to produce toxins and things like that that are going to just help those microbes survive, that's what plasmids are for, and that's what makes it really nice to have them, even though they're not necessarily needed to survive. One of the things we'll talk about is the necessary and absolute need for protein synthesis. We've got to make our proteins. This is yet another way that antibiotics, and you can see down here at the bottom of the slide, several antibiotics target ribosomes, and they target the site where we're going to make these proteins. Because if I don't make my targeted proteins, then I don't survive. So streptomycin and erythromycin and gentamicin and chloramphenicol, those are types of antibiotics that specifically know, hey, if they don't make their proteins, those microbes are going to die. Let me target that protein production, and if I can shut that down in any way, boom, microbes are dead. So the ribosomes, they aren't found on any type of endoplasmic reticulum because we don't have smooth and rough endoplasmic reticulum. So they just sort of speckle it kind of looks like someone took a salt shaker and shook all over the cytoplasm, and those little speckled granular appearances, those are the ribosomes that you can see. The ribosome actually contains 2 proteins and a ribosomal RNA, and the proteins have 2 subunits. There's a small subunit that is a 30S subunit. When you put these into a centrifuge and you spin them down, they will actually separate into their small unit and their large subunit. So the ribosome itself has a small subunit and a large subunit, a 30S and a 50S respectively. And when you put those two together, you have a complete ribosome that is called the 70S, which makes no sense, right? Because what's 50 plus 30? Well, that's 80. So you don't add those together in order to get that complete ribosome. But if I target either the small subunit or the small subunit, or in fact the complete 70S unit, I can actually alter that microbe enough to kill it. Sometimes microbes have extra things. It's extra stuff, if you will. That's not necessarily needed, but it does help out sometimes. Those are called inclusions. Inclusions can be most of the time energy reserves. Most of the time, if a microbe's going to have anything, it's going to be a way to have extra energy just on backup. We also talked about the idea of an endospore. You guys just had a discussion question on endospores, but that is a way that the cell can protect itself whenever the environment becomes unfavorable for the bacterial survival. And essentially an endospore is resistant to everything. We can't get chemicals to penetrate it. We don't get heat to penetrate it. And so when times are non-favorable or unfavorable? Unfavorable, right? Yes, unfavorable, not non-favorable. When times are unfavorable for the bacteria, what we find is that they will go into this endospore state, and it's almost like a hibernation for them, a protective type of state. And then, whenever there's some trigger, whether that be chemical trigger or physical trigger, that says, okay, it is now in favor of the microbe, and you can now come out, then it will go undergo and return back to the vegetative state, and therefore be able to now still penetrate or cause any type of illness that these bacteria may cause. Bacillus is a species that we talked about that does this, as well as Clostridium. This is a look on a slide of a Bacillus anthracis. You guys know this causes anthrax, and we talked about this before. And we talked about malachite green being that special stain. I think that endospores of this nature kind of look like an impregnated cell, if you can see that. Sort of looks like the cell is impregnated. And if you could see the cell next to it, it would not, if it did not have an endospore, it would just look like a normal type of cell. So not all species have this, but certainly the ones that do are very wicked types of species. All right, so I'm going to pause here. We're going to finish up chapter 4 together, and I'll get these uploaded for you tonight. Look for chapter 5 coming as well, because I want to make sure you guys have enough time with the material to start studying for that Big Test 1 coming up. So thank you guys again, and we will finish up chapter 4 here in just a bit.